Well, oh my, it looks like I forgot to change the title. It's not a review session starting soon, it's a normal lecture. All right, 10 o'clock, welcome back to your favorite class. Yes. Today, going to finish buckling notes, and it was just brought to my attention this morning that I had not uploaded the second set of buckling notes. So it's on Blackboard now, and why didn't you guys tell me? Rawr, okay, you should have told me that the second set wasn't up there. God. All right. Right. So the second set of buckling notes is now available on Blackboard. So if you want to, take a look at those and follow along with what I'm doing, go ahead and do that. Right. I posted a new homework on buckling. Grumble, grumble, everybody grumble. Yeah, grumble, grumble. All right, new homework, which is on buckling. It'll be due next Wednesday. So you got a lot of buckling stuff coming up next week, including this homework and your lab for next week. All right, so gonna get a lot of buckling practice over the next week. It's a good topic and a big topic for this particular class. So do that. All right. Those of you, about half you took the exam yesterday. Hopefully you thought it was reasonable. The other half, you guys are going to take it tomorrow. And it's a different exam, obviously. I'll try to get all of the exams graded by the end of the day on Friday. I'll do my best. I'm out of town and kind of have some stuff going on personally, but I'm going to do my best to get them done by Friday evening. Okay. So there you go with that for the exams. I promise by week's end. So by Sunday for sure, they'll be done and in there. All right. Any questions? Okay. If there are no questions, let's just then pick up where we left off. So last time, to remind you, we were taking a look at this example problem, and let's talk about where we were and where we had kind of left off. We were talking about eccentrically loaded columns. We're up to sort of the very end of last lecture. We were talking about columns that were loaded just generally in the center with the centric load here I'm describing as P. But the portion we're covering in class now is what happens if columns are loaded eccentrically with some other load that's not necessarily in the centroid of the cross-section at some location Q. Well, if we have some eccentric load like this load Q, we can relocate Q to the cross-section of this particular piece, the center of the cross-section, just like you do for combined loading problems, and that's going to generate moments. Here I've kind of drawn them here, generate moments in sort of in the plane here. And yes, the load on this cross section is going to generate some compressive stress, which is P on A, but also the moments that get generated by relocating that eccentric load Q are also going to contribute compressive stress of the form My over I. So now we don't just have to worry about sort of like the centric loading providing P over A, which is sort of like this compressive load in one direction. We also have to accommodate or consider what other compressive loads might come up from relocating this eccentric load to the center of the cross-section. So we talked about that, and the way that we're going to deal with that and the way that we're going to attack these buckling problems is using what's known the allowable stress method. And so with eccentric loads, we can relocate the load to the center of the cross-section, and that's going to create bending moments, kind of like I just mentioned. Then we can find the maximum compressive stress in the cross-section using your sort of combined load analysis. And that would give us the current state of stress on the cross-section, which is something like load divided by area plus this My over I term. So some axial term plus some bending term. And it's up to us to decide where the maximum compression will occur in that particular cross-section given by this particular expression. Then we want to compare that maximum compressive stress that exists on the cross-section to the maximum allowable stress that our cross-section can handle, given some of the buckling analysis that we've talked about so far. So we had this table 9-1 in the notes, which you now have access to in the notes, and that table looks something like this, just to remind you. And this table here is giving us allowable stresses, given the certain geometries and moduli and geometric factors of the beam of interest. Okay, so we calculate an allowable stress using that table 9-1, and we're going to calculate the current state of stress and the allowable state of stress separately, and then compare them at the end. So the current stress on the structure is this P on A plus My over I. And the allowable stress that the structure can handle before it buckles is given by this table 9-1. And so here the allowable stress really has nothing to do with the loads that are on the structure. It only has to do with like the geometry and the material properties. So you have to like sort of separate these two things, the allowable stress and the current state of stress on the beam. You have to sort of think of them as separate things. And then you sort of compare them at the end to see whether or not you're going to fail. All right. So that's the general idea. And when we last left off, we were going to sort of tackle this example problem. And so this example problem's in the notes, and now that the notes are available on Blackboard, you could just go to Blackboard and see this example problem. But here we are, we're going to tackle this example problem where we're looking at an eccentric load on the cross-section of an I-beam. And so we'll give a second here to just sort of recalibrate if you need it, and then we'll go ahead and sort of tackle this problem. Let's make sure I'm recording. I think I'm recording. I got my Starbucks this morning. I'm so basic. Little do you know it's hot chocolate in there, actually. I don't drink coffee. That's for adults. I'm not an adult. I'm just a big child. All right, so let's go ahead and tackle this problem. One thing that's nice is that they give us information about the cross-section already. So they've already told us what the area of the cross-section is. Yikes, what happened there? Already kind of told us what the area of the cross-section is and what the radii of gyration are. So the minimum and the maximum, and we'll talk about the minimum and maximum in just a second. Minimum, maximum. Area moments of inertia, so that's kind of nice. And just a reminder that the C variable, which is 236 millimeters here, is the distance from sort of the x-axis to the top of the flange, just as a reminder. So what we're asking for here is we want to determine the maximum safe load according to the allowable stress method. So we want, remember our allowable stress method, we're comparing the allowable stress to the current state of stress to determine sort of when these things are equal. So the allowable state of stress, remember, this is just geometry and material properties. The current state of stress are loads and geometry. Okay, so we're going to calculate these two things separately. For the love of gosh, calculate them separately. So let's attack that now. Let's first start with the allowable stress. So that's where we'll begin. And again, if we're looking at what the allowable stress is, it only has to do with the cross-sectional geometry and the material properties of the piece, okay? So the allowable stress that this thing can handle before it buckles is what we're looking to calculate. And this more or less comes from table 9-1. In your Riley book. This is also in the notes that I gave out that you now have access to, which maybe you didn't before. All right, so if we're trying to determine the allowable stress, we need to determine whether we're in the compressive range for very short columns, or in the intermediate range for this intermediate column, or we're in the slender range for very long columns. So to do that, we have to first determine what the slenderness ratio is, and then compare what range we're in based on that table 9-1. All right, so we need slenderness ratio. And to determine this, we need to know about which axis we're going to buckle. Okay? And remember that the axis about which we're going to buckle is the one with the largest slenderness ratio. Okay. So if we're looking at the axis for buckling, which is the largest slenderness ratio, then we want to know where the slenderness ratio is maximized. LE on R is max when R is min. All right, so our radius of gyration R should be minimized if we want to maximize our slenderness ratio. So if we sort of think about this, then the critical slenderness ratio is LE on R minimum. Okay, so we're looking for the axis with the smallest radius of gyration. All right, so let's go back up to the problem and sort of define what the effective length and the minimum radius of gyration are. All right, so we'll go back up to this problem statement. And here we say it has an effective length, I'll highlight this, of 6 meters. It already kind of tells us this. All right, so LE is 6 meters. It's already given that to us in the problem. That's nice. We don't need to worry about changing the value of the length of the column to accommodate for buckling or for boundary conditions. It already gives it to us. So that's nice. Now we have to look at some of the material properties and determine what our minimum radius of gyration is. And so here we have like this y-axis about which we could potentially buckle, and we have this x-axis about which we could potentially buckle. And we're not told necessarily what the radius of gyration is about x or about y. We're just told that sort of the minimum and maximum radius of gyration are the following. And we said to maximize the slenderness ratio, we want to take the minimum radius of gyration, which here is 67.3 millimeters. So that's what we'll use. So here then, our LE on R is 6 meters divided by the minimum radius of gyration, which is 67.3 millimeters or 0.0673 meters. And we'll find here that the slenderness ratio is 89.2. All right, so here's our slenderness ratio for this problem. This is the critical slenderness ratio, or the largest slenderness ratio that we have for this cross section. So then the question is, what range is this? Is it slender, intermediate, or short? Okay. And to determine if we're slender, intermediate, or short, we have to go to table 9-1. All right. So this is a steel column. We're told that in the problem statement. So a reminder here, this column was made of steel with some certain modulus. It has effective length of 6 meters. Okay. So this guy is made of steel. So we want to go to table 9-1 and look at information regarding steel columns with a yield stress of sigma y. Okay, so here we are. This is table 9-1 telling us about the intermediate ranges of steel. All right, so here we have code number 1, structural steel with a yield of sigma y. So the idea here is if our slenderness ratio is between 0 and this sort of CC value, then we would be considered in the intermediate range. And if it's greater than the CC value, we would be considered in the slender range, and we'd use this equation for the allowable stress. So the point is that we need to figure out what this sort of transitional value of CC is. So we see here to calculate what that transitional value is between the intermediate and the slender range. Here is the CC squared we're given as 2 pi squared E divided by the yield stress. Some, threshold slenderness ratio that's going to determine whether we're in the intermediate or slender range. All right, so that's something that's going to be critically important to us. So let's make perfectly clear that if LE on R is greater than CC, it's slender, and if it's less than this CC value, it's intermediate. That's what our code tells us. So that means that we need to calculate this like threshold value. We're told that the general equation for this CC squared is 2 pi squared E on the yield stress sigma Y. So then the CC is the square root of, and I'll put all the information in here now, 2 pi squared. The modulus is given to us in this problem. It's 200 GPa divided by the yield stress, which was also given to us in this problem of 290 MPa. And if you work this out, this sort of like threshold slenderness value is 117. All right, so we've got this threshold slenderness ratio of 117, and we see that our critical slenderness ratio for this problem is 89.2. And so after this calculation, we can see that in this situation, our actual slenderness ratio is going to be less than CC. So this means we're in the intermediate range. Okay, so now we're in the intermediate range. We know what equation then that we need to use to calculate the maximum allowable stress. And that again will come from 9-1. So here we are back to 9-1. If we're in this intermediate range, which we are, our allowable stress is this equation. Yield stress divided by Fs, which is sort of a factor of safety, pseudo factor of safety, multiplied by this general quantity, where Fs is given by this expression here. Okay, so a little bit complicated, but I'll copy this all down into my little example problem here. So from this, we know that the allowable stress is this sigma yield divided by Fs multiplied by 1 minus 1/2 times the quantity slenderness ratio divided by this critical value. All of this going to be squared. And we can see that we basically have everything here except we need this Fs value, which is also given by table 9-1, where Fs is 5/3 plus 3/8 times the slenderness ratio on this critical value, CC. So it'll be minus 1/8 the slenderness ratio divided by the CC value to the third power. Where this comes from, experiment, obviously. So we could do this. 5/3 plus 3/8. My slenderness ratio I know is 89.2. And this sort of critical slenderness ratio is 117. Minus 1/8 times, again, my slenderness ratio, 89.2, divided by my critical slenderness ratio, 117 to the third power. All right, after all this settles, we'll have this Fs value, which is 1.9. Now that can go back into this allowable stress equation. And we have everything else in that allowable stress equation to calculate what the allowable stress is on this cross-section before failure. So then, my allowable stress is the yield stress, which is 290 MPa, divided by this FS, factor safety kind of thing. It's 1.9. All multiplied by the quantity minus 1/2 slenderness ratio divided by a critical slenderness ratio, which is 89.2 divided by 117. All of this squared. So your allowable stress here, if you punch all this into your calculator, 108 MPa. Okay. So this is 1/2 of our allowable stress method formulation. We've calculated the allowable stress that this particular cross-section can handle before it fails by buckling. Notice, we have not talked at all yet about the eccentric load on the structure. We haven't said anything about that load P. All right, this is only based on the geometry and the material properties of this cross-section, the yield stress, the elastic modulus, right? So here we are, this is my allowable stress. Now, separately, I will calculate the critical or the current state of stress that's on the structure. This is where that eccentric load is now going to come in, and we're going to have to calculate things based on that eccentric load. Okay, so now we have to talk about the current state of stress. And that might force us to want to sort of draw a picture. So let's make a picture here. Okay. So the picture of our cross section, I'll sort of do my best to draw this, but I'm more or less replicating sort of like what's all the way up here. I'm replicating sort of this cross section here for this particular piece. And I'll do my best to do that. So that's going to look something like this. Oi. Try again. Okay, looks something like that. And if we're looking at it like this, we would have the following coordinate system that is coming off, X, Y. All right, so I'm just kind of like replicating that picture that's up above. Here. All right, so I know I have an eccentric load that's on this cross section, and it's located right about here based on the picture, and it's pushing down here with some value P. All right. And I know that it's located off of this center of the cross section. This length here, which is the length E. I think I'm given in the problem here, which is 0.125 meters. That is given in the problem. All right. So what I want to do is I want to relocate that value P to the center of the cross section, and that will generate for me a moment that acts on this cross section that increases the compressive stress at certain locations. So if I sort of look at what the cross section would look like after sort of relocating that load, again, I am great artiste. But the idea would be, okay, I would relocate to the center of the cross section, that load. But also with it now, I would generate a moment here, where that moment is simply equal to this distance E multiplied by the load P. Hopefully we sort of see that and understand that. Now, what I want to do is I want to determine where the compressive stress is the highest on this cross-section. Because wherever the compressive stress is the greatest on this cross-section is where this thing is going to fail, okay? So if you're looking at this particular cross-section, hopefully you can intuit at this point that obviously this axial load P is going to provide an even compression across that whole cross-section. So there's no one particular point on the cross-section that has higher compressive loads on it than others simply from this axial load of P. However, when we consider the bending moment here, this bending moment, if we thought about like sticking our thumb in that direction of the double arrow and curling our hand, this bending moment would give maximum compression along this edge of the bar. Okay, so along that top edge, you're going to have the maximum compression. And that maximum compression is going to be something like my over I, where y is the distance from here to the edge of the bar. With me? Capiche? That's where I'm interested in my failure, because I'm most likely to fail in buckling where the compression on that cross section is the highest. So even though I've calculated what the allowable stress is before this cross section fails previously, hold on just a second. My family's like kind of coming in and making a bunch of noise. Even though I've calculated where the compression is maximum on this cross section, and I know my current allowable stress, I need to sort of calculate what the maximum compression is at this particular location. Okay, so let's go through that. All right, so my current state of stress is going to be something like the axial contribution plus the contribution from bending. Here, this is going to be something like P on A plus the additional compression that I get from the bending moment that is applied. P is the variable that is sort of unknown in this problem. All right, so that's something that I'm actually sort of solving for in this problem. The area is given to me at the beginning of the problem. You can kind of scroll back up or take a look at that if you want, but that's 18,365 millimeters squared. And that was told to me sort of at the very beginning. I'm going to add to that this bending moment that I calculated as E times P, where E is 0.125 meters times P multiplied by Y, which is the distance to the top of the bar, which is where the compression is the highest. Remember, the compression is highest at this location, the top fiber of the bar. So this Y value is the distance from the center of the cross section to where that stress is the highest. And here for us, that's going to be, I'll scroll back up so you can sort of see the picture. That is this distance C, all right, from the center of the cross section here to the edge of this particular piece. Hold here that C is 236 millimeters. So here this is times 0.236 meters. All divided by area moment of inertia. Okay? Now, I'm given two area moments of inertia in this problem. A minimum and a maximum. I know sort of from my picture that my bending moment is going to be here, right? So I'm bending about the x-axis. But my question is is Ix equal to I min or I max? This more or less comes back to what is the definition of area moment of inertia. Now, hopefully you had some training in your 2002 class about area moments of inertia. And maybe we'll just have a little aside about area moments of inertia quickly so that we can have this discussion. And our cross-section reminder looks like this. Okay. So I want to know which is larger, Ix or Iy. Okay. Give you a second to think about it. Do we have any guesses? Anyone want to be brave enough and type in chat? Which is greater, Ix or Iy? Who's going to be brave? Caleb says Iy. Well, there's a couple of ways that we could check. You could go to the back of your book and look if, at some I-beam cross sections. But generally, we might consider thinking about I-beams for their general resistance to bending and why they are made this shape in the first place. So when you think about area moments of inertia, remember your general definition for area moment of inertia is something like Ix is the integral y squared dA, something like that, integral on the area. The idea here is that if you have small elements, you're looking at how much material is displaced against the axis of interest. So here we have a lot of material in this cross section, basically all of this material here, that is displaced very far away from the x-axis. If we're bending about y, we don't have a lot of material displaced far away from that y-axis. Hopefully this is like jogging your memory. So in general, we're going to have a larger area moment of inertia here about x because we have much more material displaced away from that particular axis. So in general, it's harder to bend about the x-axis because more material displaced from x-axis. Okay, it would make this value very large in the calculation of the area moment of inertia about x. So, which is larger, Ix or Iy? Here, Ix is larger. Oh no, did I lose my notes? I hope you guys can hear all the barking in the background. Here we are. Okay. So Here we're going to be using IX. And that's because we are bending with this bending moment about the x-axis. And that would be this maximum value here. Okay. Since the area moment inertia about x is larger than the area moment inertia about y. So here it's the I max for this particular problem, which for us, given in the problem, 7.28 times 10 to the negative fourth meters to the fourth. All right, so that was kind of a long tangent there. But here we have that the current state of stress, after working this, and this will be in terms of P, will be something like 94.8 P. Units here are PSI, where P is in pounds. All right. So notice that we have just calculated the current state of stress using like what looks like combined loading equations. And we've kept P as the unknown variable because that's what we're sort of solving for in this problem. Notice that we didn't consult table 9-1 at all when we looked at this. It was just what is the current state of stress on this cross section using like combined loading equations. All right, so now we're finally ready to go back and tie it all together. Okay, so my allowable stress from before was 108 MPa. So I'll say 108 times 10 to the negative times 10 to the 6 pascals is equal to my current state of stress. This is not PSI. This is pascals, where P is in newtons. Sorry about that. So 108 MPa equal to my current state of stress, which is 94.8 P. This is also in pascals, where P is in newtons. All right, important to know that. So all said and done, my load on the structure that would cause failure, given this maximum allowable stress method, 1.14 meganewtons. Mega. All right, that's a doozy. It's a long problem. Okay, any questions on this? I think we're going to call it here if there are no questions. Okay, that's going to be it for the buckling section of the course then. I'd encourage you to take a look at your lab and also take a look at the homework number 5, which I posted, which will be due next Wednesday. Otherwise, for those of you that are taking the exam tomorrow, I'll see you tomorrow.